Cache invalidation is the hardest problem in coding. If you update your database but forget to purge your cache, your users see old data. Always use a TTL or delete the key on every write.
The most common defense against stale data is the TTL, or time to live. This is a self-destruct timer on every cache entry. You might say, keep this profile data for 60 seconds, then throw it away. It's simple, it's robust, and it requires zero coordination between systems. However, TTL is a blunt instrument. If you set it too long, your data stays still for minutes, frustrating users. If you set it too short, your cache hit rate plummets and your database gets crushed by traffic. TTL is essentially an admission of defeat. You are saying, I don't know exactly when this data will change, so I'll just guess how long I can afford to be wrong. For many applications, this window of being wrong is acceptable, but for financial or collaborative tools, it's a non-starter.
If you can't afford to be wrong, you move to write-through caching. Here, the application treats the cache and database as a single unit. When you update a value, you update the cache first, and the cache synchronously updates the database, or vice versa. This ensures that the cache is never stale. It sounds perfect, right? But there's a catch: latency. Every write now has to wait for 2 network round trips instead of 1. If your cache is in Virginia and your database is in Oregon, your write performance will suffer. Furthermore, you've now introduced a distributed transaction problem. What happens if the cache update succeeds but the database write fails? You've created a phantom update that only exists in memory. Solving this requires complex retry logic and error handling that most developers underestimate.
Even if your invalidation logic is perfect, you can still fall victim to the thundering herd. Imagine you have a very popular piece of data, like the front page of a news site, cached for 5 minutes. At the exact second that cache entry expires, 10,000 concurrent users all hit your site. The cache says, I don't have this, so all 10,000 requests slam your database simultaneously to recalculate the same result. This can cause an instant database collapse. To prevent this, engineers use cache locking or request collapsing. Instead of letting everyone through, the first request grabs a lock, and the other 9,999 requests wait patiently for that one person to finish the work and refill the cache. It's a critical pattern for high-scale systems that protects your database from its own popularity.
In distributed systems, time is relative. If 2 different servers try to update the same cache key at the same time, you can end up with a race condition. Server A writes to the DB, then server B writes to the DB. But due to network jitter, server B's cache update arrives before server A's. Now your cache has server A's old data, even though the database has server B's new data. The fix? Versioning. Instead of just storing the value, you store a version number or a timestamp. The cache should only accept an update if the incoming version is greater than the one it already has. This optimistic locking approach ensures that even if messages arrive out of order, the final state of your cache will eventually match the truth of your database.
So how do you survive the nightmare? First, default to simplicity. Use TTLs whenever possible. If your data can be stale for 30 seconds without causing a support ticket, let it be stale. Second, use delete instead of update. When data changes in the DB, just delete the cache key. It's much safer to force a cache miss in a reread than to try and precisely update a cached object. Third, monitor your cache hit rate. If it suddenly drops, you likely have an invalidation bug or a thundering herd. Finally, remember that a cache is an optimization, not a source of truth. Your application should always be able to function, albeit slowly, if the cache is completely empty. If your system crashes when Redis goes down, you don't have a cache, you have a distributed dependency.